But congrats on making it through the semester just about. So the plan for today was just to really have like an office hours and answer any questions that any of you might have in terms of the exam. So just to be clear, it's the same. The exam is going to be administered same way as the previous two. There'll be a multiple choice part, Canvas quiz, followed by a written part afterwards. So it's going to focus on worksheets 19 through 23, but certainly it's going to include content from the start of this semester in terms of direct proof, contrapositive, contradiction, induction, all of those proof methods as well. So I want to be clear about that. So it'll be about the same length as the others. Those you've had until 12:15, and then there's been some time for uploading and stuff like that. So we'll kind of stick to the same plan. There's a typo over here. That should be, the upload should be in by around 12:30. But I'll see you on Zoom. So if you're having some issues uploading, then just let me know. Okay, so yeah, otherwise I'll just say, I don't know what is kind of useful to do with our time, but maybe I'll just kind of make some general comments and then leave it for you guys. No one emailed me about looking at anything in particular, so I didn't prepare anything in particular, but here's kind of the info guide for exam 3 that kind of just goes through the worksheets. What were some of the main ideas on those and some examples of problems that we did. So we kind of stopped on the last exam. We didn't quite get to equivalence classes. We did equivalence relations, but not the classes. So just to be clear on this exam, I'm not going to ask you to prove some relation is an equivalence relation going through the properties, but I could say, here's an equivalence relation, describe the classes to me, or here are the classes, give me an equivalence relation that would result in those classes, that kind of thing. So there are some examples about that. So here's one where there's a relation, tell me what the classes look like. And here is one which is, here's a partition, or here's a relation given in terms of a set, tell me what the corresponding partition would be. And here's one with modular arithmetic. Yeah, so that's kind of what you would be expected to do as far as equivalence relation goes. That would be like describing classes, working with integers, mod n, that sort of stuff. And then I'll just say, outside of that, we talked about functions, injectivity, surjectivity, composition, inverse. So some of these terms were from earlier in the semester. Function, domain, codomain, range, one-to-one. You actually had some questions on this on the very first exam. We had talked about some of this. And then now we added into it this notion of what does it mean to be surjective and bijective. And so here are some of the proof techniques that we could use to prove injective. And I'll say, oftentimes contrapositive is a really useful way to prove injectiveness. And then here's a proof technique for surjective. And then these are some examples. These are mostly things that have been on previous worksheets. I just kind of picked them off of this worksheet and just put it here as a reference if you want to practice it. But these are problems that we've seen already. So they should look a little bit familiar. And then we talked about this notion of, okay, if a function is bijective, then it has an inverse. What does it mean for a function to be in inverse, right? It means that when we compose them in both directions, that they undo each other. So if we want to prove that something has an inverse, that means we can either do a constructive proof, say, here's a formula for the inverse, and here's a verification that this formula satisfies these two properties. Or you could look at the function and prove that the function is injective and bijective. it has an inverse, you don't necessarily have to express a formula for that inverse. Any questions? So that was mostly what, well, some of the homework that you have due for this week was dealing with composition and inverses. And then we ended with cardinality of sets this week and last week, talking about countable, countably infinite, uncountable, those sorts of things. And so at the very end of this sheet, I did kind of pick off the information from earlier in this semester about when we just did direct proof, when we just did contrapositive proof. I don't know why this starts with step 2. Step 1, read the problem. Now you've got a step 1 here, sorry. There we go. Contrapositive proof and contradiction and induction. So I'll just say, certainly you need to know these techniques because you're going to have to prove things, and those proofs might involve these techniques. So you'll see these proof techniques like in the context of functions and countable, proving things are countable, uncountable, that sort of stuff. You'll also see some multiple choice questions that just focus on proof techniques. If I wanted to prove this statement using contradiction, what would the first line of my proof be? That kind of stuff. So, you know, we've seen those before. I would encourage you to go back and, you know, just make sure you've got those proof techniques down. That's the main point of this semester, is to come out, you know, with a good general idea of these proof techniques and be able to apply them in any math class that you're in. So that's all that's on the info guide here, is just kind of the highlights of the worksheets and some good illustrative questions that we did on some of those worksheets. But in addition to this, you know, you've got some additional practice problems that are recommended in Canvas. So I would say, you know, you want to kind of balance going back over problems that we've done in class and on homework, but also try practicing things that we haven't already done just to test yourself. And I would just be like keeping an idea of what are some general things that are kind of useful when you're doing proofs. And just a couple of comments that I'll make. Things that I look for when I'm grading is, you know, definitely you should be writing complete sentences. Avoid overuse of notation. These are not unrelated things. Okay, so in other words, I don't think I've ever used that in a proof, so I don't want to see that. I don't want to see this in proofs, right? You can say therefore or thus for this, just write out the word. You can say implies for this. So just be sure that you're writing out those words. You know, the use of notation might be nice when you're just kind of making scratch notes to yourself, but in the end, this is kind of like writing out something a little bit more formal. I'll just say label parts of proofs, such as forward direction, reverse direction, injective, surjective, those sorts of things. I look at your problems, and if you do those things, you certainly earn points. It's not like I'm looking at your problems to take away credit, but if you don't have those things, it does make your proofs harder to read. So I do like to see those things. Basically, all of this stuff is spelled out in the proofwriting guidelines worksheet, but I would just like to point some of these out in particular. Label proof techniques, if not direct proof. If it's direct, you don't need to indicate that, but if you're using another proof technique, then tell me what you're doing. Proof by contrapositive, proof by contradiction. And then just have the correct outline in mind. So when I start grading things, I look, okay, what are they proving? They're proving the forward direction. What technique are they doing? They're doing it by this technique. So then in my mind, I think, what would the very first line of that proof need to be? And so I check to make sure that kind of you started things off reasonably. So when you're writing your proof, just some things to pay attention to, and that is, don't introduce notation without defining it. So if your proof, for example, refers to X and you just throw X in the proof without saying what X is, that could be confusing. So for example, just say, you know, let X be an integer, and then use that in your proof. So just be sure you define these things before you do it. Make sure that you're using appropriate notation, meaning sets are denoted with this. That's the default for that. Equivalence classes, although they're sets, right? We use brackets for those. We use capital letters for sets. And we typically use lowercase letters for elements of sets, unless those are sets themselves. Okay, so when our elements are numbers, whatever that may be, we typically use lowercase. And so these little things actually help the readability of your proof quite a bit. So these are just some details to pay attention to. Am I forgetting something? What else have I harped on this semester? And another thing I'll say, like when you're trying to verify, like, hey, if I want to prove this function is an inverse of that, don't just say, here's the function, it's the inverse, and leave it for the reader to verify that. So just be sure that if you're claiming that some function or something satisfies certain properties, actually make sure you show that it satisfies those properties. Yeah, and I will say kind of the less work you leave for the reader, the more complete your proof is going to be. Any questions about that? So I'll just say, you know, a lot of these proof techniques, they have very clear first line, like all of these proof techniques over here. So I would say that, you know, there's this balance between having like a rigid structure and not being able to kind of freelance things versus just really sticking, you know, not having any script whatsoever. So I would think that these things help you if you get stuck. And I would just really pay attention to things in general, like when I'm proving contrapositive, you know, what should my first statement be? So, okay, we're gonna start by assuming this, and we're hoping to get over here. So kind of just keeping these general things in mind are really helpful. Okay, so what sorts of questions can I help with? You can chat them in. You can feel free to speak up, whichever you prefer. Okay, I got a question about using, you know, if you're given equivalence classes to try and come up with a relation that satisfies, that would result in those classes. So that we can certainly take a look at. So on homework, just to kind of refer back to that one, on the last homework assignment, I believe it looked like, I see, it was something like this. You were given a partition, right? That said, right, we're going to consider classes that look like this. So let's say we have a partition like this. Right, and so the idea here is given an equivalence relation, we get classes. And what's really nice about an equivalence relation are those equivalence classes form a partition. So we can think of a partition as an equivalence relation. From an equivalence relation, we get partitions. So if you're looking at this, really what we're observing from this partition is we have an equivalence class 0. So whatever we have here, well, it's an equivalence relation anyway. 0 should be related to itself. It's reflexive, but it's not related to anything else. And then over here, we can see, well, I would need this. I would need this. I would need that. And I would need that. But a lot of these things are a bit redundant because we know this is an equivalence relation. So I don't really need to say those separately. But really all that's saying here is that these numbers, first of all, need to be related to themselves. And now all I know is that -1 should be related to 1 as well, but nothing else. And so when you start to see something like this, it might be tempting to say, here's our relation. But here you would want to be careful because if this is your relation, then, for example, -1 is not related to -1. Right? It's not related to itself since the absolute value of -1 is +1. So a lot of people fix that by saying something like this would work. Just brings up a note that a lot of people wrote something like this as the relation. And I didn't take off points, but I just kind of made a comment that when you write something like this, it might not be clear whether you're saying y has to equal x and -x, whether this is like and or an or statement. So when people were writing this, I believe what you really meant to say is that we're going to say these things are related if y is equal to x or y is equal to -x, which is the same thing as that. So that's just kind of a comment on that, since that's something that you probably have thought about already when you were doing the homework. So let's just kind of look at something like this then. And this might help, although it's kind of going in a slightly different direction. So here we've got a relation. This is totally abstract question here because we don't even know what all of these things are. They're just letters. And so if I wanted to start writing out the partitions here, right? So when we think about the set, the equivalence class A, it's going to be the set of all things in our set S such that A is related to X. So X is coming from this set. So we can see over here. So I'm just going to go through and write out what are all the elements that A is related to. So it is related to itself. It's related to B. There's not an A, it's not an A. That's it, right? So A is related to itself and A is related to B. Which means, right, I don't need to worry about the equivalence class of B. They're going to be equal to each other if they're related to each other. And then we can kind of go down the next element, and this is going to be all of the things that are related to C. So that's going to be C. That's going to be a D. And that's going to be an E. And I think that covers the basis there. So from this relation, right, we would have two equivalence classes. The equivalence class for A and B, and the equivalence class C, which contains the other three elements. So the partition here would be A, B, and then C, D, and E. And notice the notation here. These little things are subtle, but it's important to note that, right? These equivalence classes use these brackets again, although they're set. So when I write it out like this is really meaning the set containing everything C is related to. So I could write it like this, or I could write it like this, but I don't want to write it like, I don't want to write this like that, right? Because that would just be a set containing one element. So just be careful about that. So that's like taking a relation and setting up a partition from that. But otherwise, if we're going in the other direction, then it kind of just it's kind of hard to generalize what you would want to do in that process. But it might help to start writing out like what elements are in the equivalence class. And if anything, if you can't write out a formula, sometimes it's not possible, at least you might be able to write out the set representing those relations. So I don't know if that helped with that one, but if not, let me know. Otherwise, I don't have any other questions in the queue. So if you've got something, feel free.
Sorry, I have a question. I think I don't understand the last thing you wrote, where you said, is it element C is not equal to?
Yeah, so this is a set. This over here is the set containing one element C. So when we use these kind of curly braces, it means set. And when we use these square brackets, it means an equivalence class. So this is the equivalence class of C, which in this case contains three elements, C, D, and E. So I can say this, which is true in this case. But if you say this is implying the set containing just one element.
Oh, okay.
Yeah.
Sorry, I think I was just confused why you wrote just the set of one element.
Yeah, so just to point out that if you change the notation, you change the conceptually what it is. So you just want to be careful about whether you're using brackets or braces. Yeah. Yeah, and sometimes it's difficult in math because we use some sets of notation for the same thing. And so you need to read context. So it's not clear sometimes whether this is the point x, y, or this is an interval going from x to y, right? And that is something that you typically need to pick up on the context. But that's a digression from for us right now. But the point here is that, yeah, this notation is important.
I
Yeah.
missed maybe the first 10 minutes of class. I was wondering if you went over how many questions were on the exam.
So it's going to be this similar as the previous two exams in terms of length. The multiple choice part will be about the same. I don't know if it's exactly 10 questions, but more or less about that. And then the written part will be as long as the previous one. So it's not going to be a longer exam than the previous ones. Yeah, as far as like exactly how many questions, you know, I think that not all questions are created equal. Some are shorter, some are longer. So I'll just say like it should take about as much time as the previous exams. Well, that's great. I guess you guys know everything you need to know. So awesome. I'll stick around. If you've got questions, you can feel free to stick around. Otherwise, I haven't gotten any others in. So that's great. As you're kind of getting ready, don't forget you've got homework due this evening. And then our exam is 11 on Monday. And I've got office hours tomorrow from 10:30 to 11:30. If you have any questions. Otherwise, I'll be checking email over the weekend. If you want to shoot me a question over the weekend, that's okay. If you write me like Sunday night at midnight, I probably won't be able to respond to you in time, but if you get it to me by like Sunday afternoon, I'll be able to respond. Okay, well, otherwise, thanks everyone for nice semester. Hopefully, one of these days I'll get a chance to see you on campus in the fall for those that are going to still be around. And good luck finishing up your classes and exams and projects and all of that. And I will certainly see you guys on Monday, if not before then.
Thank you, Adam.
Yep, no problem.
Thank you.